Hi everyone. My name is Etienne Bernard, and I work at Wolfram Research. Basically, I'm leading the machine learning group there. And today I'm going to talk about the functions, the tools that we've been building over the last years. I'm going to be quickly talking about what we before. I'm going to be mostly talking about what we're adding to this to the next version, which is 12.2, that should be there in a matter of months, I guess. And then talk also a bit about our plan, about what to do in the future. And about that, I will be very happy if you give me your comments, your opinions about what we should do. That would be great if you have some specific needs in what you're doing that help us to prioritize. Like, we have a big list of things, but that help us to prioritize one thing over another. So in the Wolfram language, there's usually, you can decompose the thing we have in terms of machine learning in three parts. One part is this, what I call the high-level machine learning, or automatic machine learning, sometimes we call it, which is a bunch of functions that are very task-oriented. For example, the main one is classify. Classify, you give it a list of examples that are labeled, like, it's an image and this is a tag. It's a griffin, this is an image, and the tag is dragon, an image, and or the class, I rather say, is centaur in that case. And you just run classify on this set of examples. There's a bunch that I'm missing, by the way. There's like 20 more here or something like that. You don't have to specify the method. You don't have to specify the pre-processing. It figures these things by itself. And then you can use that to classify new images, and more generally, new example. It doesn't have to be image. It's all sort of things. It's audio, text, and a bunch of numbers, categorical variables, a mix of all of these things. And as you will see, we added a graph time series recently. And then there's function to predict a number instead of a class. There's functions to learn the distribution of data. And so it's unsupervised learning function. And you can do synthesizing missing values with that, detecting anomalies. There's function to clusters, to find clusters in data. And dimension reduction. So this is a bit similar to learn distribution, is to find a reduced representation of each of the example, in a way to find the manifold on which the data lies. Okay, so that's the high-level machine learning part. And then we have a lower level, which is our neural network framework. And so this you need to specify the model yourself, contrary to this, where you can just run the function. Here you need to create the model or use a model that already exists, such as here. Here it's using a net model. And then you can modify it so it suits your applications. It's very classic, by the way, when you're doing neural networks, you just take a neural network that already exists, changing usually the end of the network just to make it satisfy whatever constraints you have, and then training it on your data. And so that's the simplest training we can imagine. It's just a linear layer. It's the simplest neural network you can do. And so there's still some automation in the sense that here the optimization method is not specified, or the batch size, or all these things, or learning rate is not specified. You can specify them, but there's a bit of automation, but still it's more low level than the high level machine learning functions. All right, so, and the last thing is the application that we do with these tools. So for example, image cases, something that finds objects and classifies them in the image, or text cases. So here it says, find all the city, country, and date, and return the string, the interpretation as an entity, and your confidence in a way that it is indeed a city, a country, or a date, and that would do the job. And then there's a bunch of net model that I talked already, excuse me, like if I do, actually probably we can see a bunch. Exactly. So you can see there's a big list. Oh, it's behind the screen. Yeah, exactly. So there's many pre-trained networks, some of them that we just imported, some of them that we train ourselves, and that you can use. Like that's the network of email identify, for example. Okay, which looks like this. Actually, you can note that we also changed a little bit how the layers look. I don't have the latest version, so I think it changed a little bit, but now when it's square, it means that there's some learnable parameter inside, and when it's round, it means there's no learn parameter. And then also the icon changed. Also, let's see if we find one. No, they're all the same. Anyway, you'll see, but when it's a layer that contains other layer, the border is bold, and I mean, we'll see examples. Actually, we can see them here. Here, the border is bold because they are new. They are, you know, exactly. There's another thing inside, and in that one as well, there's another graph inside. But here, there's nothing inside, so it's not. It's kind of the leaf of this sort of tree of layers. All right, cool. Let's see. There's questions already. Can you go into visualization tools? I guess that's what I just did. And yes, I will upload the notebook at the end, for sure, for sure. I don't have time to do it right now. Maybe I should have done it before that. Okay, so what's new in high-level machine learning? One thing that is new is that when you use classifier measurements, instead of this object that is not super informative, it returns a nice report. So you can kind of see usually what you want in this report without needing to query this measurement object for extra properties. So just to recall, classifier measurements, you give the classifier as the first argument and the test set as second argument. And it evaluates the classifier on the test set and compute a bunch of measures. So this is a report, but it's actually a computable thing. So you can use this report to ask for the accuracy and a bunch of other properties, not just the properties that you see here. This is really just for display. You actually have a lot of properties you can ask this report. And you have the same thing for predictor measurements. Okay. And all right. Just checking if anyone raised their hand. Okay, other thing that I think many people will like, it's measurements from predictions. Because in the past, the first argument had to be a classifier. But now it can just be, let's say, the classification, in that case, the classes that are predicted by the classifier. And this is still the test set. I don't need the input though, because I just need to compare with the output. But I mean, you can put the input if you want, but it's not necessary anymore. And here I can compute the accuracy between these two sets, basically. And I can also have the report as we saw before. You can also give the probabilities for each class. And in that case, it will also compute probabilistic metrics, such as here mean cross entropy. And you can also give that as a categorical distribution. This is a type of distribution that we added in the 12.1, I believe. So I don't know if you're familiar with it. And yeah, so that's, and the nice thing is that it doesn't have to be a classifier or a neural network, the first argument. So you can have your custom classifier and you can still do all these measures easily. And same thing for predict. So you can do predictor measurements. These are the predictions. These are the real values, and that's the report. And again, you can put, instead of the prediction as a unique prediction, you can put the prediction as a distribution. And it will also compute things like mean cross entropy, which is a probabilistic measure. Okay, see if there's any question about that. So, how can we extract from decision tree algorithm learned by Classify? I see. So you cannot, but we are thinking of having a function that is just for that. Classify also has a bunch of preprocessors, like there's a bunch of things going on in this. So it's no one be like a nice decision tree that you can extract from a classifier function. But we're doing a function that will just restrict itself to just a decision tree, because we know that that can be a nice way to have an interpretable model. In some cases, it's useful. That's something we are actually thinking a lot. I mean, it will be there soon, I think. To create a compiled function for netrain. Yes, and we will see that right after. Can I deploy the netrain function for particular net architecture in order to have a C function that can train? Basically, yes, although you have to do a bit of work. Like I will talk about it after. We have an exporter to ONNX, which is kind of an exchange format for networks. And from there, there's a lot of tools to convert this ONNX network to various things. And you know what? I bet there's something to convert to a C function. But you know, you can convert to many things. Okay. So next thing, probability calibration. That's something that was close to my heart, and I finally did it. Not that the story is that interesting. Okay, so let's train a network, and here I use an internal option. You know, you don't have to really care about that. I just prevents the model from being calibrated. And here I'm going to compute to visualize a reliability diagram, also known as calibration curve. And on the x-axis, you have the predicted probability. On the right, on the y-axis, your actual probability. So this means that, let's say this point, this means that we gathered every time the classifier predicted 60% of chance, let's say it's around here, 60% of chance of being a given class. Okay, so each time the classifier says, I believe it's 60% of chance of being whatever class. And then we looked among all these examples that it says 60%, when was the classifier right? And apparently it was right 99% of the time. So this means that this classifier was seriously underconfident. Seriously underconfident. And you can have the opposite, where a classifier is completely overconfident, where you're going to say, well, I believe it's the right class with 99% of chance. And actually you realize that among all these times it says 99%, well, it's only 80%, let's say, or 50%. Usually they are more, I mean, when you have a neural network, for example, they're typically overconfident and not underconfident, but this is the case where it's underconfident. And so yeah, you can have a diagnostic with this reliability diagram, which, by the way, if you look in other libraries, it's usually what I call now the classic reliability diagram that I don't like so much. It's just the probabilities are between, it's a flat scale, it's a linear scale, you know, between 0 and 1. And you have these S curves and so on. But if you have in sort of logit scale, where, you know, like the thing close to 0 are expanded and the thing close to 1 are expanded as well, it's much nicer to visualize, I think. It is usually a straight line. And here you cannot really see what's going on here and here. I mean, in that case, nothing's happening here, but. All right, so now let's train without this option, and you'll see that automatically Classify calibrates its result. So we also added that now, not for all method, but all the, oh, actually it's not that great, but still it's much better. Now you see it's much closer to the line, perfect calibration line. So here it was like 90% of belief, and the result was maybe 80, you know, 80 something, 89% or something. So now classifier is better calibrated, which I think is an important thing. Okay, sharp values. So this is something to, I mean, this is just a start. It's very experimental. It's something to explain the decision of the predictors and the classifiers. And here I'm going to get a data set, predict the wine quality as function of all these features, and then predict the quality of this wine, which by the way was 6, but is going to be ignored, and it predicts 5.6. And then I'm going to ask why was it 6? And this gives a bunch of number and basically says, well, the acidity contributes kind of like you know, there's a mean prediction over all the examples, and it says, well, that there's the acidity contributes negatively of 0.11, 0.12 to the prediction. And if you sum all these values and you add the mean, it will give this prediction of 5.6. And I'm not going to talk further because Jesse is talking about it, so he can explain to you how this works. Okay. And but as I was saying, yeah, it's just the beginning in this area. We hope to have more things later. Graph features. So before you couldn't put graph into machine learning functions, and now you can. So here's an example of feature space plot. I just created random graph from various graph distributions, and you can see that it correctly kind of separated the graph depending on their on the nature, so to speak, on the, yeah. These are Bernoulli graph, Barabasi graph, and uniform graph. And I can do the same thing with Classify. So here I label them. I say this is a bunch of Bernoulli graph, a bunch of Barabasi, a bunch of uniform, and then it can predict which one it is. Which, by the way, for this example is pretty easy. I should make it a bit harder, but this is pretty easy to have a classifier for that. So yeah, so you can use that, I don't know, maybe for molecules. I mean, you need to do a little bit of preprocessing. Maybe next time we should add molecule as a type as well. And you can do that for a bunch of other applications. Time series also, we added some feature extraction and therefore feature, let's say, understanding for time series. So that's just an example of feature space plot. Yeah, by the way it works is it does compute a bunch of properties about the graph. So things like, actually I can probably show you, if we dig in the inside of the classifier, I can show you what it does, which graph extract features. Yep. So you see it compute, some classic properties such as, is it directed, is it a multigraph, is it empty graph, is it weighted, is it blah, 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 blah. And then a bunch of numeric properties, vertex count, graph density, graph reciprocity, and so on. And also some statistics about the connectivity of each node, like if they have a lot of edges or not. So, quantiles of this list of let's say edge count, and things like that. So it's a bunch of statistics. So it's not like it's a neural network that is, learning a nice representation for the graph, which theoretically is possible, but you have to have many, many more graphs. So this is kind of the sort of brute force approach that actually I find already efficient. And we did kind of the same thing for time series. So it computes, a bunch of Fourier transform, a bunch of things, detect the peaks and things like that, and make features out of all these measures. And I think it's already going to be pretty useful for a bunch of applications. Okay, let's see if there's some questions. On X refer to train net. Yes, C function that I can fit learning data that will return the weight. No. This definitely not. You need to train with the Wolfram language. Okay, can you discuss support for fitting classifiers to training sets with badly imbalanced class numbers? That's interesting. That's something that Classify is not very good at that currently. So we have to do something about it. Basically, the trick is to reduce the dimension. So, I mean, if you want to do it by yourself right now, what I would do is you take your data and you forget about the classes. You just use dimension reduction that we saw in the beginning. Oops. Dimension reduction to find a small representation, and then you train on that. And that would avoid the example that have a small number of somebody talk to me. Let's see. on the chat. Okay, and that would avoid the class that has a small number of examples to kind of overfit. You can also learn the distribution. Like the extreme version is like for anomaly detection, where you learn the distribution of the input and you just use the PDF as a feature for classification. So it's kind of extreme dimensionality reduction. So that's things you can do for extremely balanced classes. And hopefully we can integrate these sort of things into Classify soon. That's a good point. Okay, let's see, there's some other questions. And yep, so Classify, Kaggle Titanic. No. Yeah, so this is, oh, it's interesting. Titanic, I guess. So usually on small data sets, it tends to change the method that it uses. It is fundamentally stochastic the way it searches for the best method. So one thing to make it more consistent and better is just to increase the sort of search time. So you can use time goal. You can use the option time goal to tell Classify. So let's look in the documentation. And then you can tell Classify, well, spend a long time to do your business, which for that case is not really useful, but, and then it will do much more search. It will try many more methods, many more hyperparameters and so on, and find a good classifier. And in that case, it should be more consistent. I expect that it's because it has a small, like by default, it's a little bit aggressive on the time. I can also put performance goal to quality to alleviate that, but yeah, I think by default it's a little bit aggressive on the time, and that's why you have different, especially on small data set. I mean, small data set, you also have the fact that you don't have enough examples. Okay, so then we have new methods that I won't go in detail about it. This is something about Classify. This is two methods for dimension reduction. This one, multidimensional scaling, is pretty well known, and probably we should have done that before. But anyway, it's there, dimension reduce. And that's an example of multidimensional scaling. It's extremely classic. It's just try to preserve the distances. That's it. That's the only thing that this thing is doing, is you have an original space, high dimensional, and you embed all this data in the low dimensional space, and you try to have the distance between each pairs be the same in the feature space than in the original space. So extremely simple, and it works pretty well. So, okay. Now let's move to the neural network framework. And so ONNX exports, which is super useful to deploy your neural networks, let's say on a cell phone, which is what Geoffrey did, and he's going to talk about it today. I won't spoil it, but the idea is you export to ONNX, and then from ONNX, either you use the ONNX runtime that many devices support, or you convert to kind of the specific format that a given device wants, such as Core ML for an iPhone. Function layer, there's going to be a talk about it as well, so I'm not going to talk it too much. Jérôme, I'm going to talk about it today. And but basically, it's a way to put regular Wolfram language code to construct layers. So it can be a very simple code, like just a function, min, and that's an example, or it can be a more complex function. In that case, you see, this is just a vector of numbers that are fixed, right? And this is a vector of numbers, but that is learnable. That's just the initial values. So that's a learnable array. And that's a new thing as well, net array, that we constructed for function layer. And so you can create arbitrary layers like that. And you see how it looks. You can see the function, you can see the graph. So this is compiling to our neural network framework. All right, so it's doing a sort of conversion to a graph. That's how it works, which means that it's limited to static computation graph. You cannot have if statement, for example, which for 99% of application is not an issue. Basically, so yeah, everything you can do here, you could do it with a graph, but often for many applications, it's nicer to write it as code than as a graph. For example, to share layers. for sharing layers, it's much nicer to use regular code. All right, compiled layer, very related. Matteo is going to talk about it. Basically, we leverage the new compiler for the Wolfram language, which is function compile, and where you create a function and you have to specify the type very well. You know, that's the rank of the array, the type of the data, and so on. Then you put your function, and then you can do compiled layer and just use it. And this is not compiling to our framework. This is really keeping it as is. So I think it's converted to LLVM first. So it's going to be slower, of course, but you have more freedom. And for example, you can have if statements if you want. Although at the moment the output shape is fixed. So it's not absolutely, let's say, universal. We start working on adding new array processing functions, which is not really machine learning per se, but since we start to define networks with regular code, it's necessary to have really good array processing function to write these networks. So the first one we did was array reduce, which is kind of a way to perform an operation like min on whatever axis that you want. Here it will perform on the rows actually. And I think if you do that, it's on the column, exactly. Okay, that's a little explanation of what it does. Let's not go into the detail. You can also do on many axes. It's like aggregation layer for the one that knows in the neural network world. Okay, new function. Okay, maybe let's not. Okay, this is just new layer. You can check them out, and a bunch of new net models that you can check on the website. I see the time has already passed. I guess we started a bit late. So let me look a little bit at the question and then we'll go about what's next. If I randomly split data 80, like 2080, and then run classify, I get a classifier function. If I have 100 function, how can I combine the function into a single composite function? Well, my guess is you compute the probabilities and then you do a geometric mean of the probabilities. That's what I would do. It's just a very simple way to combine classifier functions. There's no built-in way. I think actually there is one, but it's a bit hacky. So I'm not going to talk about it. Okay, so what's next? In the high-level world, we just started to explore and build things in the domain of model and decision explanations. So the most famous are LIME, SHAP. So SHAP, you see, is the first sort of quite experimental version that you will have in 12.2. I must say that it's still not the perfect thing. Like we have to, which is, yeah, for some reason that Jesse probably will explain. Adversarial example, counterfactual sort of things, you know, like give me an example that give a decent decision, but it's not too far from the original example. And this is give me one that is also realistic. Give me a realistic example that would have given another decision that is close to my current example. We need to automate more dimension prediction and clustering in the same way as we do for classify or learn distribution. It's kind of a different automation procedure, and this one is, I mean, classify and learn distribution are superior about that. Reinforcement learning, that's something that would be really nice. There's not that many applications, to be honest, but that would be pretty cool to have it nevertheless. Maybe something called policy optimize, I don't know. Also detection function, that's something we need to get into, I think. It's basically, you know, inside a time series, find the anomalies, or inside an image, find objects. And you need to learn from data how to do that. And so, you know, classify is just classifying one thing. And here it's more, and there's a bunch of functions, of task, which is just find inside a text or image or sound or time series and find stuff inside these things. Then for neural net, extension of function layer, of course, like probably this is going to be, and I think when it's really, really good, it might be renamed something like net function, something like that, and to really program whatever you want. And that's a neural network and it will learn. And that would be super cool. That's where we want to go. Reinforcement learning, we'll be thinking of some tools also to help. Maybe just the classic learning methods will have their function, like gradient policy optimized. Device object is our way to define an environment. External net, something to not convert a network to our framework, but just keep it in its original thing. So for example, Onyx network that would just convert it, stay Onyx network. And what's nice is that there's some network that cannot be converted to our framework. But with that, it won't be the case anymore. And so you can evaluate. You might not be able to train them, but you might at least evaluate them, or do inference on them. And also on any device, usually the Onyx runtime will be cover more device than our own inference engine, let's call it. Ending space array tree graph training, that would be great. Training on Mac AMD cards. I mean AMD GPU in general, which include Mac. Maybe something about training easier on the cloud. That's something. And last thing is we're starting to go a little bit into what machine learning can do for statistics and data mining. So for example, I think probabilistic programming, that would be very cool. And for people to do Bayesian statistics with that, like they kind of define their experiments, in a probabilistic way, and then they can infer, if this group is doing better than that group, and automatically do data imputation and all these sort of things. Also, data relation extraction, that would be something like association rule learning. This is super classic, but there's a bunch of things we're thinking about finding relation between features, this sort of thing. Like anything that is interesting in the data, I would like to be able to extract it and tell you about. Okay, I think that's it. And I'm going to look at the questions again. And when are the new features expected to be available? Well, all of that, what's new in 12.2, something like a month. I mean, at least that's our current plan. And this one is going to be for the next version, which I think is something like in April of 2021. Yeah, but I don't promise that we'll have everything for this next version. Okay, I think we're good. I don't see any other questions, so thank you everyone for being here. Bye-bye.